So, welcome to the conclusion of our analysis of what limits bacterial growth rate. So, what we did over the last few vignettes was to tackle a really interesting puzzle. And the puzzle was what sets the growth rate of bacterial cells? In other words, from a synthetic biology point of view, you could imagine setting yourself the challenge of trying to construct a bacterium that would divide in under 5 minutes, just for example. And in a certain sense, what we've done is to try to figure out what are the pressure points. Where would we have to actually dig in order to accomplish that? So, in this final vignette, what I want to do is I want to just kind of give a recap of what we've accomplished. So, as I say, we started out with a puzzle, and then I would say that the main methodology that we used was order of magnitude thinking. And that order of magnitude thinking is epitomized by a few key ideas. So, one of them was Wilson on the desert island. That is to say, what could we figure out by pure thought? And I think you've seen that, by knowing the size of a cell and then imagining that its density was the same as that of water, and then knowing what fraction is dry mass and so on, we were able to figure out a lot of things, like how many carbon atoms there are, and then how many ATPs that would imply need to be exploited. From a arithmetic point of view, although I didn't say it explicitly until now, we really introduced this idea of few times few equals 10. Okay, so f squared is 10. And I'm going to use that repeatedly in this course. It's now become a thing. So this is just a simple way to try to do arithmetic without getting obsessed with too many decimal points, and with confidence at the same time that the outcome of our estimates will be good to within less than a factor of 10 if we carry this out. Another thing that we didn't talk about, but I want to just introduce here, is the idea that if I don't know something, my best guess when I'm making an estimate is what I will refer to as the square root bound rule, where what we do is we guess a lower bound, we guess an upper bound, and then we take the square root of their product. And what that really amounts to is averaging the exponents. So this is really the same as saying 10 to the a plus b over 2, where 10 to the a is guess number 1 and 10 to the b is guess number 2, and then we take the square root of those two things. So that ends up basically amounting to the idea of averaging exponents. And another way of saying it is we're finding the middle on a log scale. So that was the arithmetic part of this. The next thing I want to say is that we exploited really beautiful data. And in this case, the data that I'm thinking of is the proteomic data. So we were able to query the results of mass spectrometry and ribosomal profiling in a way that allowed us to figure out how many copies there are of the various proteins, such as sugar transporters, ATP synthases, RNA polymerases, and so on. And that also turned out to be extremely useful. And we closed with some tentative intuition. And what I mean by that is that we leave with a contending hypothesis. And the contending hypothesis is the idea that the production of ribosomes is rate limiting. So here's kind of a recap of the things that we looked at. So, we posited all sorts of hypotheses about what might be rate limiting. This is a little bit higher resolution view than the example I gave before. So we thought, well, maybe nutrient transport is limiting. We thought that perhaps the cell wall synthesis could be limiting. We thought, part C, that maybe energy production would be limiting. And then finally, we attacked the question of the central dogma. And in the end, we found that in all of these cases, that in a certain way, parallelization was the answer. And when I say parallelization, what I mean is that we can always increase, for example, the number of transporters, and so we can bring in carbon backbones in parallel rather than having to do this in a sort of one at a time fashion. And what we concluded is that the production of ribosomes can't be done in this in a parallel fashion, in the sense that one ribosome has to make another ribosome, and there seems to be no way around that. So, to summarize the entirety of the calculations that we did, this little diagram is intended to, first of all, at the top, just remind you of how one goes about measuring the 20-minute division time. One of the ways of doing it is using microscopy, as I show you here. And then on the bottom, these are all sorts of different hypotheses that we tendered for what might control bacterial cell division time. And it's kind of neat because what we do is we show how much there is to copy or to make, to synthesize. We talk about how many machines there are that are available to do the task, and we comment on how fast those machines do their respective tasks. And so, the upshot of all of that is, as I said before, that we end up concluding that somehow it's the ribosomal proteins that are really the hypothesized rate limiting step. So where we are in the course is that this really served as a launching point for getting a feeling for how to do this sort of order of magnitude thinking. It was also a nice biological puzzle. I'm not saying that we've unequivocally resolved it, but we did take a much closer look at the macromolecular contents of cells, where they come from, how they're synthesized, and the rates of these various processes. So what we're going to do next is we're going to turn to some vignettes about scaling more broadly. So thanks for your attention.